We are going to present here some of the available strategies for outlier detection. The goals are that you, 1, become comfortable using several outlier detection algorithms in your workflow, and 2, that you are cognizant of the potential consequences of doing so. As a strategy to help understand the behavior of outlier detection, we will demonstrate artificially adding outliers to a dataset. We will start off with a note on outlier versus novelty detection, then we will introduce some of the available algorithms. The working data will be the avail customer retention data with simulated outliers. We will also demonstrate the importance of visualization at this stage in the workflow. Does a new observation belong given the data that we already have? If not, it could be considered an outlier. Novelty detection algorithms assume that outliers are not present in the training data, and they are concerned with the detection of outliers given new data. If we assume outliers are present in the training data, then the algorithm falls into the category of outlier detection. It can be used also for novelty detection once trained. These algorithms come up frequently when dealing with extremely unbalanced data in a supervised learning context and when models are deployed and there are implemented quality assurance mechanisms. Here are some of the most commonly encountered outlier and novelty detection algorithms. There are a number of points to keep in mind. The elliptic envelope may break or not perform well in high-dimensional settings, for example, where n is less than p being the number of dimensions. However, you can use PCA or another dimension reduction technique first. For the one-class SVM, the radial basis function kernel is usually chosen, although it needs to be manually tuned. All of the methods will need to be adjusted or tuned to work for your data. For this reason, visualization becomes an essential way to ensure it is working as expected. Here we create a data frame with train, test, and outlier X data. Using that, we make a PCA and TS&E projection, one for each. Notice that we are projecting with all of the data at once rather than separately for the train test split. Also, you may have noticed that it can be tricky to get feature names from a column transformer, so here we show you how to do that for this particular case. The PCA and TS&E embeddings both clearly resolve the outliers as being different. It also appears that TS&E has resolved more of the data structure given the number of groupings. Investigation with more specifically labeled plots could help us understand the nature of the different groups in both plots. In this example, we trained and evaluated the detection algorithm in PCA space, but sometimes the original feature space is best. Note that TS&E is great for visualization, but PCA is a more stable projection, which is important for a consistent threshold. This code is an example of how you could tune a novelty detection algorithm. Tuning these algorithms to work well in anticipation of new data will remain a challenging data science task for the foreseeable future, but workflows like the one presented here can speed up iteration time.